It is sometimes said that trees are the lungs of the earth. They are certainly, along with plankton, the planet's most important translators and moderators of incoming energy. The complex relationship that trees have with radiation, precipitation, and the atmosphere drives much of life on Earth. Such is the interwoven nature of the relationship trees have with so many other forms of life that many people see trees and their interdependent organisms as functioning more like a single being than as a collection of separate entities. You could also include other life systems such as the soil, which trees build, bind together, and shield from the impact of rain, wind, and sun. Given the importance of trees, it is often godsmacking how poorly we treat them. We continue to destroy forests at an alarming rate, which not only affects the air we breathe and adds to global warming, because trees take in carbon dioxide and other greenhouse gases. We also suffer the knock-on effects of soil erosion, water loss, salted soils, and drought. Across the world, regardless of political ideology or religious persuasion, countries are cutting down trees seemingly with no heed for the consequences, all for the sake of making a quick buck. And it is no exaggeration to say that the destruction of forests will cause societies to fall. Without trees, we cannot inhabit the earth. You cannot breathe money, after all. Sure, there are some token efforts at ameliorating the destruction wrought for newspapers, packaging, and all the other products that use paper and cardboard. But none of them are as effective as preserving the ancient forest that we already have. A claim that for every tree we cut down, another is planted, obscures the fact that the influence of a seedling on the environment is very different from that of a mature tree, which may be hundreds of years old. A young forest will have a different relationship with precipitation, wind, and temperature than an old one. As with so many parts of nature and their influence on the planet, we need to understand how trees function in relation to the atmosphere. Then, perhaps we will realize the integral part that they play in our lives. So let's take a closer look at trees and their energy transactions. A tree's biomass. A tree is, in effect, an amalgam of many biomass zones, and each tree can be thought of as a self-regulating ecosystem of its own. The different parts of the tree, the stem, the canopy, the branches, the roots, and so on, have different interactions with the environment. The tree stands in soil that is, at least in part, made of itself, its leaves having dropped to the ground and decomposed, their energy in turn having been reused in multiple ways by everything from bacteria and fungi to birds and mammals. Many such plants and animals have a symbiotic relationship with the tree, receiving benefits while helping the tree in return. A bird, for instance, may get food by eating the tree's fruits or berries, but will aid the tree by depositing the fruit seeds in another part of the forest, serving to propagate the plant. Meanwhile, a wallaby, attracted to the smell, will eat a fungus on a tree root. The marsupial gets nourishment, but the fungus spores the wallaby ingests become activated in the animal's digestive system, ready to thrive once they are released via its dropping. The fungus itself may help the tree root more effectively absorb moisture and nutrients from the soil, while countless insects make their homes in the tree, in turn pruning it and decomposing surplus leaves. So, like the rest of life on Earth, a tree can be considered as an entity made up not only of its material self, but also the relationships it has with everything else in nature. The biomass of the tree is the base on which all life in the ecosystem is built. It is a conglomeration of biomass and free agents engaged in cooperative beneficial relationships. In fact, there is some evidence that even within the material fact of the tree itself, it could be viewed as a dependent web of individual parts. Some scientific research suggests that the branches on a tree may be subtly genetically different from one another. One branch may be genetically coded to flower before another, for instance, and the way different parts of the tree respond to energy inputs can vary. Such differences may be slight to the naked eye, but may help us to appreciate trees as even more complex, fascinating, and essential than we ever have before. The effect on wind. Trees are both affected by wind and, in turn, have an influence on how wind behaves at a local level. Trees in locations where strong winds are persistent have developed strategies to withstand the ravages of the wind. For instance, as wind speeds increase, many trees will shift the position of their leaves and branches so that the least surface area is exposed to the winds. Others send roots down deeply into rock crevices to anchor themselves, while others still, where root depth is limited, spread their roots very wide to provide a more stable platform. When winds rise to more than 32 meters per second, a tree is all about simply holding on for survival. In a forest, you will typically find the species that are better adapted to withstanding the wind located on the edge. Certain types of tree have developed special cells within their stems and branches that allow them to cope with the bending and compression that comes from being moved by the winds. while others expose light-colored undersides of leaves to the wind, so replacing light energy with kinetic energy. The wind also brings other elements into contact with the trees. When wind streamlines coalesce over trees, air density and temperature can increase. On the lee side of forests, cooler air may well figure more prominently as the streamlines diverge again. The difference between low and high pressure air, and so between warm and cool air, can play an important part in rates of evaporation from trees. The wind can also carry particles of material within it, such as ice, dust, and sand. Some tree species, such as palms and pines, have evolved thick bark to protect themselves when the wind flings such material against them. But forests also act as nets for such particles, capturing them and filtering them from the air as it passes through the forest. As designers, we can use this facility to protect our site from dust and even some man-made pollutants if they are a problem in the local area. When the material that is caught in the net of the forest is organic, it can provide a useful source of foliage for birds and other animals. In turn, birds and animals can support extra organic material to the forest, which provides nutrients for the trees, such as the carcasses of prey animals, and plant material from other areas. Another example of the tree is a cooperative entity, interacting with other species to provide benefits to all, a lot like a guild. When we design for our site, we can look at how trees are shaped by the wind to determine the prevailing direction of the wind and its strength. When winds are persistent, trees may be deformed permanently, growing in certain directions, and we can read these shapes to reveal the history of wind on the site. There is a scale that has been devised to categorize wind speeds by the effect on tree shape. It's called the Griggs-Putnam Wind Energy Index and has 7 levels. Level 1 refers to winds of between 3.3 and 4.2 meters per second. Below this speed, the effect of wind on trees is negligible. It causes brushing, with branches and needles bent slightly away from the wind and the crown of the tree deformed just a little bit. Level 2, for wind speeds of between 4.3 and 5 meters per second, causes slight flagging, where the tree is noticeably more asymmetric and the small branches become bent. By level 3, when the wind is picked up between 5.2 and 6.2 meters per second, you see moderate flagging. That means larger branches are bending away from the wind. A wind speed of between 6.3 and 7.5 meters a second signals that level 4 has been reached, with strong flagging the result. At this level, all the branches on the tree, large and small, are bent away from the wind. At level 5, sees winds of between 7.6 and 8.5 meters per second causing a partial throw, meaning that the trunk of the tree remains vertical at the base, but is starting to bend away from the wind nearer the top. When prevailing winds reach speeds between 8.6 and 11 meters per second, trees perform a complete throw, with the entire trunk now bent significantly leeward. That's level 6. Level 7 refers to winds averaging over 11 meters per second, and these create the effect of carpeting, with trees forced to grow in a prostrate manner, appearing more as shrubs, with their canopies virtually horizontal to the ground. This effect is most common where trees are exposed to strong onshore winds on coasts. Such an index is a good visual guide for reading the way wind and trees interact on your site. And with the information it provides, you can then design accordingly to get the effects you want, such as planting a windbreak to deflect cooling prevailing winds away from your house, or diverting winds to a turbine generator to produce renewable energy. The effect on permaculture. The evaporation of water from trees, either as surface water in the leaves or through the process of transpiration, a part of photosynthesis, can be considerable. It has been estimated that a medium-sized elm tree may get rid of almost 7,000 kilos of water over the course of a day. While evaporation occurs during the day, condensation happens at night. The leaves of the trees provide the perfect surface for moisture to condense on as they tend to be cooler than surrounding objects. Given all the evaporation that has gone on in daylight hours, and this cool air rising from the trees into the air that is passing over the forest causes condensation, and given that it has been estimated that leaves are themselves comprised of 86% moisture, and that water absorbs more heat effectively than air, it is this moisture interaction that is the main way trees modify temperature. The tree is typically cooler than the air and the surrounding soil by day, lowering the surrounding air temperature and warmer than it at night, so emitting heat and causing local temperatures to rise. We can use this modification of temperature by trees in our designs. Placing a small clump of trees upwind from a house can serve to keep the temperature of the house more stable, for example. Thus can be further enhanced by the strategic use of water bodies, as air moving over water is cooled in summer and warmed in winter. Even the choice of tree species can have an impact upon temperature across your site. Trees and shrubs with reddish leaves reflect red light waves, while those with whiter leaves, such as birch and wormwood, can reflect up to 85% of the incoming radiation. Such plants are, then, very useful for moderating warm summer temperatures, either for other plants or for your home, and can generate cool air currents that can divert to where you need cross-ventilation. Trees and precipitation. Besides modifying temperature, feeding and creating soils, and providing the atmosphere with oxygen, trees play an important part in another essential driver of life, precipitation. There are 4 ways that trees have an impact on precipitation levels. They are the compression of wind streamlines and increased turbulence and airflow, condensation phenomena, snow and meltwater effects, and providing material that serves as nuclei for rain to form around. Let's take a look at each of those in turn. Compression and turbulence. Wind flows across forests. About 40% of this air goes into the forest, while the remaining 60% is deflected over it. That 40% that goes into the trees is generally brought to a standstill by around 1,000 meters. All the energy of the wind and the dust, moisture, and other elements that it was carrying become absorbed by the forest, resulting in increased temperature and humidity, around 15% higher than the ambient air outside the forest. This slowed air in the forest is virtually dust-free because negative ions, which are the result from all the myriad organic life processes occurring in the forest, are released into the air and cause the positively charged particles of dust to clump together, becoming heavier and falling from the airstream. Dust and particles are also filtered by the trees, particularly at the edge of the forest. The trees at the edge of the forest bear the brunt of the force of the wind, protecting the less resistant species in the center. These edge trees also protect the other trees from dust abrasion and windburn by salt. Forest edges should therefore be considered permanent features of protection for other species and should not be cut down. We can also mimic this edge break effect when establishing a forest by planting a windbreak to serve as the forest edge, diverting the wind from the younger trees as they establish themselves in our forest. If the air entering the forest is hot, it gets shaded, cooled, and humidified. If the air is cold and humid, it gets warmed, dehumidified, and gradually released up out of the canopy because warm air rises. This can often be seen in misty spirals reaching up from the tops of the trees. In such ways, the trees modify heat and humidity to make life tolerable for all the organisms in the forest. The 60% of the wind that is deflected over the forest gets compressed. Streamlines converge, and this compression effect can extend for a distance of over 20 times the height of the trees, while also serving to create more water vapor in the air. Both things make rain more likely on the leeward side of the forest. This deflection also causes more turbulence in the wind, forcing it into a series of spirals which further adds to the compression and the likelihood of rain falling. The spiraling effect is repeated downstream many times after the initial deflection, describing a series of Ekman spirals, which we discussed in the video on pattern. This repeated compression and spiraling, combined with the Coriolis effect on the Earth's rotation, also means that the wind direction can change, all as a result of the wind interacting with trees. A single tree line or hedge can cause the wind direction to shift by as much as 15 degrees. You can imagine then that if you wanted, you could institute a series of them to create a large spiral of wind that turns back on itself, something that does happen in winds out at the sea in the form of cyclones, although not due to trees, of course. Condensation phenomena. On coastlines, the relatively warmer land causes cooler, water-laden ocean air to flow onshore in the evenings. When this warm, humid air flows over the cooler surfaces of leaves, or rocks, glass, or metal, some of the moisture condenses on their surface, aided in part by bacteria on the leaves which provide nuclei for frost crystals to form around. This condensation can actually provide the forest with far more moisture than it receives from rainfall. In fact, on some slopes, coasts, and islands, as much as 85% of the moisture forests receive come from condensation. If you just think how much leaf surface a single tree can have and multiply it by the number of trees in a forest, you can imagine how much potential there is for condensation. And the good news is that all types of trees act in this way. It is this effect that supports the rainforests in places like Chile, Scandinavia, and Tasmania, as well as the redwood forests of California. It hardly needs saying that if you remove trees from an ecosystem, the impact on moisture levels can be dramatic. Indeed, some other locations, deforestation has turned once verdant areas into drought-ridden landscapes, all within the lifespan of a person. The removal of the trees not only significantly reduces condensation and rainfall levels, it also causes rivers to dry up, swamps to petrify, and soil moisture to disappear. Onshore humid airflow can also cause increased condensation by the formation of advection fog, when the moisture-laden air moves across the cooler surface of the leaves, causing the air temperature to fall and the dew point to be reached, when the air becomes saturated. This is particularly apparent over mountainous and hilly areas near the coast, and in such places this fog is the primary source of moisture for forests. All the moisture that the trees return to the air through evaporation and transpiration, the release of water through special pores in the leaf surface, contributes greatly to cloud formation and hence the composition of rain. As air moves over the forest, as much as half the rain that falls inland can be from the trees, the remaining half being oceanic moisture which, when the wind first hit the coast, comprised the entirety of the clouds. Indeed, almost 3/4 of the water that passes through the forest as rain, condensation, and fog is recycled by the forest and returned to the atmosphere. The remainder leaves the forest via surface runoff and groundwater, eventually reaching the streams. Forested areas return 10 times as much moisture to the atmosphere as bare ground, and double the amount returned by grasslands. Some estimates put the percentage of all the moisture in the air that is provided by the release of water from trees and plants at 50%. The rising of warm, humid air from the forest causes clouds to form as a mixture of forest and oceanic water vapor. The air rising from the trees has organic particles around which water droplets coalesce and make rain more likely. In fact, in some areas, such as the Amazon rainforest, twice as much rain falls on the forest than is contained in the incoming air that flows over the forest from outside. This means that half the rain that falls is generated by the trees themselves in a loop, the water cycling from the clouds to the trees, to the ground, then up through the tree via the roots into the sap to be transpired from the leaves into the clouds, and so on. Again, it doesn't take much imagination to consider what deforestation will do to such cycles of moisture. We see now how removing trees can have drastic impacts in terms of desertification, not only in the areas where the trees once stood, but also inland, where the influence the forest had on weather systems was significant. We need to make conscious, determined strategies to preserve the forests that we have and to establish new ones.